Thank you once again, everyone, for joining in to our July Tech Talk with the GIS Trek. We're going to talk about working smarter, not harder, with Python. I am a firm believer in using process automation as much as possible. Once we know that this algorithm or this workflow functions correctly, then let's go ahead and automate that sort of thing. Now, one of the common workflows that we have at the GIS Center is number one, prepare and analyze literally thousands of GIS layers files. Normally, we get into the thousands because we're looking at, as you can see there, LiDAR tiles, individual LAS files, or LiDAR bare earth digital terrain model tiles, TIFF files, thousands of pieces of aerial imagery tiles, climate rasters. We're working with climate data even just before I got onto this webinar, doing some analysis on climate data across the Western United States, wildfire difference normalized burn ratio or wildfire fire severity layers, NDVI layers, you name it. We deal with a lot of layers, tremendous number of those things. Now, these data often cover, as you can see, they're very large spatial extents. For the most part, a lot of our data covers the entire Western United States, 11 states, and a broad temporal extent, decades. For instance, the climate data, that's a better example, that we're using begins in 1980 and runs through, well, right now what we're using, through the end of 2023. That's a tremendous amount of data, and it is daily data for that entire Western United States from 1980 through end of 2023. You can do the math on that we're talking about thousands and thousands of layers. Our data preparation steps include, number one, knowing what is the spatial reference system of this layer and the next layer and the next one. What's the pixel size? Are they all the same? Well, oftentimes for our spatial analysis, the science that we're doing, we need to make sure that we're dealing with very, very uniform and consistent data. So the same pixel size is really important. What's the data type? What's the bit depth? Our LiDAR data needs to be 32-bit floating point data, et cetera, et cetera. We need to know that before we jump into our analysis so that our analysis is done correctly. Now, you can do this manually. Open up ArcGIS Pro, navigate to the catalog pane, find that layer that you're interested in, right-click the layer, choose properties, expand those sections, right? We need to get some information from the raster information section. There we go. Cell size we can see is in fact 1 meter pixels. Yes, it's 32-bit floating point data. We have LZW compression, all this good stuff. This is good, but now I also need to look at the spatial reference system. Let's expand that one. Okay, it is in NAD 1983 Idaho TM, the state standard. All this stuff. And I need to scroll down on this LiDAR data because I need to also make sure that the vertical datum is correct, right? That we're dealing with NAVD 88 expressed in meters. Got to have that. That's all got to be done correctly. And so we're talking about thousands of layers. I might need to make notes on this. Oh, hold on, this one's wrong. I guess I got to correct that one. And then for layer number 2, repeat. Layer number 3, repeat. How about layer number 1000? Repeat. Does anyone want to do that? You oftentimes might just start sampling. Let's just check a few of them and see how it all plays out. But you probably won't catch the oddball 1 or 2 or however many that are not correct. Or we can use Python to do this. There is a command, a function in Python called describe, and it really does what we want it to do. You can look up all the details about describe using this link right over here. And boy, it does what we want. In fact, describe can be used on so many different types of items, right? Any item, every item that ArcGIS can use can be described. We could, as I'm alluding to in my example today, is going to be looking at raster data because we have so much of that. But you can also do this for point, line, and polygon feature classes, entire geodatabases, and so on. Now, we can also combine or build upon the functionality of describe using the walk function. The walk function. That's sort of where we go in and what we used to call recurse through different folders and all of their subfolders. Okay, so the walk tool is also, or walk function is also really, really helpful. Here is an example of some code. Now, there's not too many lines to this thing, right? Normal stuff, we just import ArcPy, the system, the operating system. And then what I'm doing right here on, well, the fourth line of actual code, I'm setting a file, right? And I'm telling Python to open a brand new file called describe. Gee, ain't I imaginative am I naming? Well, it's going to be the results of my describe routine. And it's going to be a .csv, so it's an ASCII file, comma separated values. And this W, this doesn't mean walk. This W means it's being opened up for write, W-R-I-T-E. Now, I'm going to write something to it, and here's my output line. I'm going to write, and these are going to become column headers because we can open up our CSV in Excel. We can open it up in ArcGIS Pro if we want to. So these are my column headers or field names. What's the file name? What's the spatial reference system? What's the vertical datum, data type, all the stuff. And it keeps going. It actually keeps going to this side over here. And then to actually force it to write this, we use a print command, right? So here's the print command, and it's taking the contents of output, string. It's opening up the file right there, and it's then filling in these parameters. What's the file? Describe.csv. And now it says A. A is for append. If we don't have an append on this, then every time we write, it's going to write over the top of the previous line. So append is necessary. Then I'm going to jump into this. This is just a header, right? This is going to set things up so the file is very readable and understandable for you. Here's my workspace, and I'm going to walk through. I'm going to walk through this workspace right here, and it's my Bare Earth, all my Bare Earth TIFF files for northern part of Idaho, and there is a lot of them, right? Rasters, this just tells Arc what to do, and I'm putting in a placeholder right here. If it cannot find a vertical datum, if a vertical datum has not been defined, a little bit of error trapping here, I'm going to force it to tell me it's unknown. If I don't put that in there, the vertical datum will just be blank, and that doesn't really tell me too much. I want to know that it just couldn't find it. So this will be unknown. If it finds an actual vertical datum applied to one of those TIFF files or the TIFF file that it's looking at this time, then unknown is replaced by the actual vertical datum. Now here's my walk command, telling it to walk or recurse through this workspace. Top down is true, and this sorting. And the data type, what's it looking for? I'm looking for raster data sets. So under the describe command, you would then tell it, you might change this to a certain feature class or whatever it is. Yeah, that's all described pretty darn well for you in that documentation using the link I showed you before. So now I'm doing some for next loops effectively. For this directory path, this directory name, and all these different file names in walk. Now we jump into a nested for next loop or for loop for file name, this thing. Well, one of these in file names, right? So it's got just one file name, and it says that is my current raster. What is that file name? I'm building this, and this is going to end up going into my file column right here. What is this? So that's the name. What is the spatial reference? What is the data type? Is it compressed? What's the compression type? LZW, LZZ, none. What is the no data value that's being used? Do we have a consistent no data value that's being used? That can sometimes be important to us as well. What's the minimum and maximum Z value of those pixels, right? So this will help me know that it's in the correct range of values. You know, a vertical datum can be defined as NavD 88 meters, but the actual data stored on those pixels could really still be in feet. So if I'm seeing minimum and maximum Z values that are way beyond what I would expect for meters here in Idaho, this tips me off to that problem, lets me know all about that, right? How many rows and columns are there in this particular raster layer for the LiDAR stuff? That's not terribly important that they are the same. They will not be the same, but some other layers, yeah, they need to be the same. So I write that out as well. What's the pixel size? I want all of my raster LiDAR data to be 1 meter. I want all of my satellite imagery, Landsat satellite imagery had better be 30 meters or something's wrong with it, right? So I need to see all this stuff. And then we're going to go in and do a little routine here. It's going to try, and this is because sometimes vertical datums will not be assigned. Vertical is, describe this out for this current raster, spatial reference system, vertical coordinate system name. If it fails, this is about the only place it'll ever fail because you don't have to have a vertical coordinate system applied to it, especially if it's climate data. Well, if that's the case, we're going to output what we do know, and that word unknown will stay in here, and it'll be written out for us. This is that print that actually causes the write to occur. There's the append, and then I'm telling it to continue. If it doesn't, or if it does function here, that will cause it to drop down, and here's a new output. It will not write the same thing twice. Continue will cause it to go back up here. Output, current raster, same type of thing. But now, in this instance, which is most of the instances for our LiDAR data, the vertical datum is defined. And of course, it's doing the same routine here, writing it to the describe.csv with the append. Okay, let's jump in. How do I run this thing? Well, it's, you know, a Python script is actually just text. It's just an ASCII text file with a .py extension on it. And I build these things using IDLE, the ArcGIS Pro IDLE. So I know where this thing is, right? I find it on my hard drive. I locate the script. I'm going to right click on it and I'm going to choose Edit with IDLE ArcGIS Pro. Then if I need to modify it, I just ran it over the northern zone of LiDAR data, and now I want to run it another time for the eastern zone. Okay, I can make a small edit to it. If you do make any edits to it, many of you I think already know this, save those edits first, and then you can run that script. And normally I just press F5 from my keyboard, and away it goes. In a minute or so, and it all matters how many files it needs to read through, how large those files are. But once it returns, it has finished the job. You can then close up all that Python script window and then open up the CSV. As you can see, I've opened it up in Excel, and actually from Excel, I'll press F12 on the keyboard, and then I save it as an XLSX. Just because I can retain the width of the columns and make it look a little bit better so I can refer to it more easily next time. But there we go. This is exactly it, right? Here's one of these TIFF files and all the different TIFF files. There's the spatial reference system, vertical datum, float, 32-bit floating point. You get the idea. All this stuff. It's just all right here. And I can skim through this. I can scan through this thing in maybe a minute or so. And if I find something that's not right, well, then of course I know which one or two or three files need to be fixed before we go on to analysis or before we put those things on the web for other people to use. The time required, as I already noted, the time required for that Python code, it's going to take a little bit of time for it to run. Not very long. Again, more files that are in that folder or set of subfolders, the longer it'll take. The larger the files, the longer it'll take. But normally we're only talking about a couple of minutes. Certainly much faster than the time it would take you to do it manually over even 100 of those individual files. Now, the Python code itself, I can't tell you that it took me 30 minutes to write it, because months ago I started this thing, and it was really simple. I just needed to know, are these all in floating point, 32-bit floating point data type, something like that. So I did the describe tool, and then I said, gee, it would be nice if it would go into all these subfolders. So I discovered the walk tool and perfected that, made that thing work. And then I'm like, well, gee, it would be nice to know this and nice to know that. So I've been building this thing over the months, and so I can't tell you how long it took me to write this thing. But don't worry, right? You can download that exact same script, use it as a template. If you want to change some of those commands to describe vector feature classes, well, you've got the shell, you've got the template. Just go ahead and download, either by taking this URL right here, or take a shot of this QR code. That will get that started for you. You can download that thing, just that real simple one little file inside there, and then you can make use of it exactly as we did, or as I walked you through this thing. I worked with this in 3.2.0, 0.1, 0.2, and now I'm also using this exact same Python tool in 3.3.1. So it's cool. It still works. It didn't break over these different versions, and hopefully it'll keep going in the future. So that is my work smarter, not harder, and leveraging Python to help you out. Are there any questions?